In this video, we are going to kind of change direction just slightly. I mean, we've been talking about series for quite a while. And eventually, we are going to get back to series, but before we do that, we're going to kind of step back a little bit and talk about something that's really, really important, Taylor polynomials, right? And how I'm going to introduce this is to remind you of something back in Calc 1 where you learned about linear approximations. So again, here's just a quick refresher. Let's say you have a nice differentiable function, y equals f of x, and we know and then we can pick any point. Let's say we pick a point, let's say that x is equal to a at that point, and we can draw our tangent line at that point, and try to do a pretty good job there. So there's our tangent line. And the theory back then, the idea is when you are close, right? So if you were to kind of zoom in on this portion of the graph, right, where you have the tangent line, the closer you get to the point of tangency, the harder it is for you to tell the difference between the curve, which is in white, and the tangent line, which is in blue, right? So yeah, you know, the slope of the tangent line is one of the first things that we learn how to compute using calculus, right? And then later on we learned that, yeah, we can just call this also, or use this tangent line now as a linear approximation. And the concept is this: if you have a difficult or challenging sort of function to work with, and you are willing to give up some accuracy, and you have to do lots of things with this function, maybe find its roots or something like that, and it's really difficult to work with. Well, if you're willing to do to give up some accuracy, you could instead approximate f of x by this tangent line. And so let me remind you what the formula that we use for linear approximations. You would take the function value at that point, that's your f of a, and then you would add to that the slope of the curve at that point, and then you would then multiply that by x minus a. And the concept is this: when x is close to a, then the original function can be approximated by the linear function, your tangent line, your linear approximation. All right. So what is our goal now, right? Well, our goal is to improve this approximation, right? And there are other ways that you can approximate functions, but we want to focus in on how we can use polynomials. And we like polynomials for several reasons, right? Even though they might be a challenge when it comes to like factoring and finding the roots, a lot of our standard operations in math, right, many of them are simplified if we are working with polynomials. Now, by simplified, I don't always mean that it's now easy, but at least we know a little bit more when we're working with polynomials. So that's our goal here, is to maybe improve um, the accuracy of our approximation. And another way of saying it is we would like to reduce the error in our approximation. Maybe not just working with linear functions, but what about quadratics? I mean, look at the shape of this particular curve here, right? I mean, this curve in total doesn't look like a line, right? But this portion of it kind of looks like a parabola. So what if we could find a parabola that passes through that point and is sort of a better fit? And then, okay, a parabola is great, but look, again, look at this curve in total. Maybe a third degree polynomial that passes through the exact same point, that has the exact same slope. Maybe we could find a third degree polynomial that does something like that, right? And that's the concept behind Taylor polynomials. And he figured out a really nice formula, that's not too difficult, that would give us a way of extending this concept of using a polynomial, right, starting with a linear function to approximate our f of x. All right, so how do we do this? Okay, so I'm going to simplify the problem. Again, I don't just like giving you a formula. By now, you should know that that's not how I work, right? The formulas, especially if you know the concept behind the formula, even if you didn't see the formal proof, if you even get kind of a sketch proof, sometimes we call it in math a heuristic, just kind of talk through how things come about, it kind of sticks a little bit more, right? Let's make it sticky so it sticks into that brain of yours. All right, so here's what we're going to do. So to simplify the problem, I am going to change this from x equals a to x equals 0. Right? So we're going to simplify it that way. And I want to emphasize a couple properties, for instance, that the linear approximation has that we would like the other approximations to have, but then add more properties to it, right? So for instance, I'm going to compare L of x versus f of x, right? So if I plug in, so let's say, let's look at the function value at the point of tangency. So if I plug a into my linear approximation, well, think about what would happen. Everywhere there's an x over here, I would have to replace it with a. Now, f of a is a constant. That's just your function value. The slope is a constant because it's a linear function. And then here I would have to plug a for this variable. And what would happen is that this term would cancel out. So I'd have the slope times 0, and I'd be left with f of a, right? So at x equals a, the linear approximation has this function value, which is the same if I look at f of a, right? So these are the same. So what this little observation tells me is this. L of x and f of x, they pass through the exact same point. Now you might say to yourself, duh, that's how we have that's why we call it a tangent line. Yes, but here I'm just focusing purely on the property, not so much on the graph. So L of x and f of x have the same function value at x equals a, right? Okay, now let's look at the derivative of both of these at that point, right? So let's see what happens when we differentiate L prime, or I'm sorry, when we differentiate L, and then let's see when we differentiate f. The whole idea is that f has a derivative and so forth. So let's write down, so I'm going to keep the little blue equation there, and I'm going to write down what the derivative of this function would be. When I differentiate L, because f of a is a constant, I will get 0. So L prime of x is 0 plus, and then this is a constant, but it's a constant multiple, so f prime of a comes down, and then when I differentiate the x, I'll just get a 1. When I differentiate the a, I'll get a 0, so I have times 1. So that means the derivative of our linear approximation is f prime of a. Okay, that kind of makes sense because it's a line, and we know that the derivative represents a slope, and the slope of a line is a constant, and yeah, that's what we end up with. So that makes sense. And then when we look at the derivative of this function now evaluated at a. So let me write the important line now. So this is saying the derivative of the linear approximation evaluated at a is the same as the original function the derivative of the original function evaluated at a. So I'm just going to put that over here as well, right? So what this observation tells me is that L prime and f prime of x have the same value at x equals a. So geometrically what this means is that the linear approximation and the function, they both, if we put these two together, they both pass through the same ordered pair with the same slope, right? And that is an important concept. So when you're building a linear approximation to a function at a particular point, you need the linear approximation and the function to pass through the same point. That's why you use the ordered pair. And you also want them to have the same slope. So you want the slope of the curve to be the same as the slope of the line at that point, which is why you use the derivative. So, but what if we wanted to use more than just a line? Then we would have to add more properties of this, because if you think about it, this is all you need to define a line. You need a point and a slope. If you want to define like a quadratic or a cubic function, you need more properties. So I'm going to write down the general idea that's used now behind these Taylor polynomials. So here's the general idea. So since we're moving beyond the linear, right, and we're moving into like polynomials in general, I'm not going to continue using the letter L. We're going to switch to P for polynomial. So I'll say P sub n, right? We use this symbol to represent the nth degree polynomial that we are going to use to approximate this function. So let P sub n be or in fact, I don't need to write the b, that's what those three lines, so we're just using this to represent, is defined by, so the nth degree polynomial that approximates f of x at x equals a, right? And what do we want? What we would want, if we wanted to extend this idea to have this be a good approximation, we want this polynomial such that it will have the value of all the derivatives, right? It's from the 0th derivative, which means the original function, up to the nth derivative of this polynomial. We want it to have the same value as differentiating this function n times and plugging in a. So let me write that down. So we require, this is what's going to help us figure out what this polynomial looks like. And I'll write it like this first. We want, if we were to differentiate this polynomial n times, so I'll do it like this, and then evaluate it at x equals a, we would want to get the same number as differentiating the function n times and then evaluating at a, right? So not only do we want the function value and the first derivative to be equal, but we would want all the derivatives up to the nth derivative to be equal, and that will give us a way of figuring out this polynomial, right? So how on earth do we do this, right? So for simplicity, what I am going to do is to say that we are going to, and again I mentioned this earlier, let's just to give you an idea of where the formula comes from. Let's say that we want the approximation to occur at x equals 0, right? So just for simplicity, right? So for simplicity, let a equal 0, all right? And we'll see what happens. So what I'm going to do is write out in general what an nth degree polynomial looks like, and then can we come up with a formula for those coefficients, because that's what we need. We need a formula to tell us what are the coefficients in our polynomial, much like the formulas that we came up with for our linear approximation. But we didn't have to do much work for that. So an nth degree polynomial looks like this. It's a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus, and then I'll write another term like this, n minus, so this being our subscript, so n minus 2, and then you have, again, the power of x that goes down, and then that pattern continues, and then I will have a sub 1 times x, and then plus a constant term, all right? So it's a little hard now when we don't know what the degree is. But let's go ahead and say, just so that we can see the pattern, and then I will generalize it. Let's write down what the nth derivative is, right? So well, first let's start with our first derivative. So if I differentiate this once, what happens is that power comes down, the coefficient comes down, and I have a sub n times x to the n minus 1. This comes down, so I'll have a sub n minus 1 times the quantity n minus 1 times x to the n minus 2. And then now this power comes down, so I'll have that coefficient that comes down, this power that comes down, and then I have to reduce that power by 1, so it becomes now n minus 3. And that will continue, and what happens is when I get to this term, I'll just be left with this a sub 1. So it looks like this, a sub 1. But then my a sub 0 goes away, right? Let's see if we can write down what the second derivative is going to look like. And then once we do this, after this, I'm going to write down the nth derivative of this polynomial. So when I differentiate again, this a sub n comes down, the n comes down, the n minus 1 comes down, and then I'll have x to the n minus 2, again subtracting 1. And then this term I would have a sub n minus 1 times the quantity n minus 1, bring down that power, and reduce that power by 1. That's our power rule for derivatives. So that's n minus 3. And if I write this one down, you will end up getting a sub n minus 2 times n minus 2 times n minus 3, and then x to the n minus 4 plus dot dot dot, and then I'll write, so this one will go away, and what I'd be left with, you notice, look at the pattern. In the original polynomial, you go down to a sub 0. In the first derivative, you go down to a sub 1. In the second derivative, you're going to go down to a sub 2, right? The coefficient of the term that was right before this one, right? So if you notice what happens, each time and let's focus on this higher power term now. Each time I differentiate it, I would just bring down the original power. And it would keep going until I get to like x to the first power, because we're starting with a polynomial. So eventually we'll get an x to the first power. And when I differentiate that, I will be left with just the coefficient alone. Right? The coefficient alone. So what happens is the nth derivative of an nth degree polynomial looks like this. You'll have the original coefficients, a sub n, then you'll have the original power, and then the power from the first derivative, and then this will be, meaning the highest power, I should say, from the first derivative is n minus 1. Then the highest power in the second derivative. Then you'll have the highest power in the third derivative. And then you'll have the highest power in the fourth derivative, dot, dot, dot. And then what you will have is just, let me do the plus. And then you will have, after differentiating n times, think about what's going to happen to that power. You're going to be left with just a constant. Because what will happen is you'll have just an x to the first power, and then when you differentiate it again, you're going to be left with just a 1. So that 1 will come down, so I'll do this, times dot, 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 times a 2, times a 1. Right? So this is what happens to the first term. Now what's going to happen to the other terms? Well, if you think about it, the other terms, those would go away because they would have a power that is less than that highest power. So technically, after differentiating my polynomial, my nth degree polynomial, n times, all I am left with is this constant, right? All I am left with is this constant. Okay, so how does this help? Well, so now if I go to evaluate, so therefore, if I take this nth degree polynomial and evaluate it at 0, for instance, then I would still just have a constant. Right? And let's look carefully at that, that coefficient to begin with. In fact, let's look carefully at this expression. We have seen this recently, right? In fact, usually the factorial function is introduced when you learn about the ratio test, because you now start working with factorials, and if you look carefully, what I have in red is actually n factorial. So I have this is n factorial. So this is what I would get if I differentiated this polynomial n times and evaluated at 0. This is my constant. And what we want now, we want this to be equal to the nth derivative of our original function, also evaluated at 0. Right? Now, when I say 0, it's like, okay, 0 is helpful, but what if we don't, for a second, want the tangent, the point of tangency to be at 0? What if we just kept the a, the original a, right? What if we didn't make this assumption, right? Well, in general, so now that I know that the nth derivative of our nth degree polynomial is just going to be a constant, this implies something even more helpful, that if I were to evaluate this nth derivative of my polynomial at a, it would still give me a to the n times n factorial, and we would want this to be equal to our original function evaluated n times, differentiated n times evaluated at a. All right? Okay, so why is this helpful? This is helpful because look at what a sub n tells us. A sub n is the coefficient of x to the n, right, in our original thing. So if I could solve this equation for a sub n, it gives me a way of figuring out what these coefficients are. Right? Now remember, my assumption here is that we were evaluating this at 0. When we state the formal theorem, right, it's going to look a little bit different, but it's going to make use of these coefficients. So let's solve the equation that I have here highlighted in green. Let's isolate to see what those coefficients have to be. So solving for a sub n, we get this equation. So let me write the equation down. It says it's a sub n times n factorial is equal to the nth derivative. This is the property or the properties that we want our polynomial to have. And then now I can divide both sides by n factorial. So a sub n is our nth derivative evaluated at a divided by n factorial. And this would be true for not just the nth derivative, but all the derivatives, right? So in other words, I would use this formula for n equals, oh, let's just say it like this, for all derivatives up to and including the nth derivative. So for all derivatives up to and including our nth. So if I just wanted a third degree polynomial, then I would stop at the third derivative. Including the nth. All right. So this formula here is what Brooke Taylor, English mathematician, he came up with this formula to say, okay, if you now want to extend this idea of a linear approximation to now maybe a quadratic approximation or a cubic approximation, this is the formula that you would use to figure out those coefficients, right? And he showed, and his method actually allows for not just the finding out the approximations at x equals 0, but at x equals a, which is, again, consistent with what we did in Calc 1. So here is the theorem, and in the theorem, you'll see this formula that comes up. And this is Taylor's theorem. Well, actually, this is just for the approximation. His full theorem not only gives you a formula for the coefficients, but it also talks about the error term. So I'm not going to do too much with the error term right now. This is just the theorem that tells us how to form our Taylor polynomials. And then we'll do a quick example at the end, maybe using something like e to the x, right? So it says, let f of x be n times differentiable, meaning you can differentiate it lots of times. So differentiable at x equals a, right? And that's what we need, right? So at least that many times we should be able to differentiate it. The nth degree, so the nth degree polynomial that approximates f of x at x equals a is given by, and here is the formula. So I'm going to write it out long term, or actually I'm going to write it out, long way. So the nth degree polynomial, and this is what Taylor says. You start with the function value because you want to make sure that it passes through the exact same point. Then you add the first derivative times x minus a. That looks all familiar, right? In fact, what the Taylor polynomials do, they take advantage of the stuff that you've done before. If you wanted a quadratic, this is the term that you would have to add, and I'm going to go up here now and make reference to this formula for the coefficients. So the coefficient for the second derivative, for the quadratic term would be differentiated twice, evaluated at a, divided by 2 factorial, and then you multiply it by this to the second power. So this is what this power here gives you a quadratic function. It's just a slightly different way of writing your polynomials, but some people actually believe this is a lot more efficient. What if you wanted a third degree polynomial? Well, then you'd have to go up to the third derivative. Look at what this formula tells us. Again, if n is equal to 3, you'd have to differentiate 3 times, then plug in your a, and now this time divide by 3 factorial, and then you'd multiply by the quantity x minus a cubed. And then this pattern would continue indefinitely, so it would be plus dot 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 plus. Then you'd go up, if you wanted an nth degree polynomial, this would be the coefficient of that term, that last term, if you will, evaluated at a, divided by n factorial, and then you'd have x minus a to the nth power. And this is Taylor's famous formula that now, in one swoop, we can come up with approximations that are much better than just linear functions. All right. So instead of just coming up with this result, let's do a quick example, and I'll choose a function that is fairly easy to differentiate, and let's find the third degree polynomial just so that we can make we can get a good sense of the process. So I'll just say this: find. And I'll use our notation here, p sub 3, so this polynomial, that approximates, and here I'll pick a function that's easy to differentiate, something like e to the negative 2x, and then let's pick it at x equals 0. So at x equals 0. All right? And let's look at that polynomial. So right away, because it's asking for the third degree polynomial, it means we're going to have to differentiate our original function 3 times. So let's go ahead and write that down. So I'm going to state the original function. Here is the first derivative using our chain rule. Here is the second derivative, again using our chain rule. And then here is our third derivative. So negative 8 e to the negative 2x, right? So we have our derivatives. Now let's look at what the formula says. We have to evaluate the function, the first, the second, and third derivatives all at the point of tangency. So let's plug 0 into all of these. So the function evaluated at 0 is e to the 0, which is 1. The first derivative evaluated at 0 is negative 2 times e to the 0, which is negative 2. The second derivative evaluated at 0 is 4 times e to the 0, that's 4. And then the third derivative evaluated at 0 is negative 8 e to the 0, that's negative 8. So what have we just found? We've found, essentially, we've found parts of the coefficient. So we found this number, we have this number now, and this number now. So all that's left to do is to kind of put it all together, and then for these terms, remember to divide by the factorial. All right? So here is the third degree polynomial that approximates our exponential function as long as we stay, or is a good approximation to this exponential function as long as our x is close to 0. So our function value is 1, and then it's going to be plus. Our derivative value is negative 2. So I'm not going to simplify it right away. I just want to see where everything is where, so that you can see where everything is going. So f of a, or I should say f of 0, f prime of 0 times x minus 0. If we stop there, that's just a linear approximation, but we want more. So we're going to add, the next term now is going to be the second derivative divided by 2 factorial times x minus the point of tangency squared, right? That's what makes it a quadratic, but we want even more. We want a cubic. So the cubic term now is take the third derivative, which is negative 8, divided by 3 factorial, and then multiply by the quantity x minus 0 cubed. All right? And let's simplify it and get this polynomial. So we'll bring down our 1. So the next term is a minus 2x Now, 2 factorial is 2. 4 divided by 2 is 2. So the next term is 2x squared. We got that. And then let's write down now the cubic term. 3 factorial is 6. Negative 8 over 6 reduces to negative 4/3. So then this is minus 4/3 x to the third power. And that's now our third degree polynomial that approximates our original function at x equals 0, right? So if we're calling this a polynomial, it better look like a polynomial, and it looks like a polynomial, right? And there you go. So that's the famous Taylor polynomial formula that is really useful, and we'll work on some examples definitely in class. That oh, I just saw where I misspelled approximate, so it should be s, not x. There we go. And here's our polynomial. So in the next video, we're going to see, well, what if we extend this? What if we go from a polynomial to an infinite series? Could we do such a thing? Well, tune in and find out. See you in the next video.